Hello everyone, this is the first of a series of videos dedicated to chemistry of non-aqueous solvents. We are going to be looking mostly at acid-base chemistry. In general, we're going to be looking into how we can predict the acid-base behavior of typical acids and bases in water, how they behave in those non-aqueous solvents. And specifically, we're going to be looking at the following solvents: ammonia, hydrogen fluoride, sulfuric acid, fluorosulfonic acid, sulfur dioxide, bromine trifluoride, and dinitrogen tetroxide. We'll also be looking at the properties and uses of supercritical fluids, molten salts, and ionic liquids. As usual, this topic is divided in several videos to make it easier to follow. There is a wide variety of non-aqueous solvents. You have protic solvents. For example, I'm giving here hydrogen fluoride, sulfuric acid, or methanol, or alcohols in general. There are also aprotic solvents, and I will discuss what I mean with protic and aprotic in a future slide. And I'm giving here the example of dinitrogen tetroxide and bromine trifluoride. And then you have solvents that we could consider coordinated solvents. They will be able to make complex ions. For example, acetonitrile, diethyl ether, or acetone. And here is just an example of several possible non-aqueous solvents you can use. Typical organic molecules like diethyl ether or THF or diglyamine, or something like this one, this compound made of two ions, which is an example of an ionic solvent. You can have protic solvents, and we call protic solvent a solvent that will undergo self-ionization and will produce protons, hydrogen ions. So it will have a similar behavior to what water does. And if you remember what would be the self-ionization reaction of water, which is the basis of pH and acid-base chemistry, you produce hydrogen ions and hydroxyl ions. So a protic solvent is one that undergoes self-ionization and will release protons. An aprotic solvent is one that either does not self-ionize or will not form protons. There's also the issue of hydrogen bonding, like water exhibits hydrogen bonding, and other non-aqueous solvents also exhibit hydrogen bonding. Ammonia, alcohols, well, I mentioned here ethanol, but any alcohol in general. Being able to form hydrogen bonds with the molecules that the solvent is solvating, it will influence their ability to solvate particular ions or molecules. It would be a good thing if for solvating particular substances. Hydrogen bonding also affects the properties of the solvents themselves. Physical properties, the boiling point, vaporization, viscosity, physical properties that will be affected by the fact that that compound, that solvent, can form a hydrogen bond. In the same way that the physical properties of water are dependent on the fact that, or are influenced by the fact that water can form hydrogen bonds. A couple of things we look at when we're looking about the properties of a non-aqueous solvent or a solvent in general is the relative permittivity and the dipole moment. Relative permittivity, which is traditionally called dielectric constant of a solvent, is a measure of its polarity. So the higher the dielectric constant of a particular solvent, the more polar it is. Traditionally, it was called dielectric constant, and you will see it referred to as dielectric constant in many books and publications. The current thinking, or the current terminology, the most appropriate one, is relative permittivity. Relative, it means because it's relative to vacuum, to permittivity in vacuum, in space. It is a dimensionless constant. It's just a number, and it depends on the temperature. Here's a table of the dielectric constant and the dipole moment of various solvents. And here you've got the line that corresponds to water, which is what we normally compare as typical behavior, that water is our comparison for all these discussions I'm going to be doing in the next few slides. There is a difference between relative permittivity and dipole moment, even if, you know, in principle, you might think that they measure the same, the polarity of a compound. It's not that straightforward. The dipole moment of a solvent, the dipole moment of a compound, is a microscopic property. It's a property of the molecule, and it's based on the separation of charges, the electronegativity of the atoms that are involved in the bonds, that produces a polarity of the bond, and therefore a polarity, potentially a polarity of the whole molecule. The dielectric constant is a macroscopic property. It's a property of the solvent, or a pure sample of that compound. So dipole moment is a microscopic property. Relative permittivity, dielectric constant, is a macroscopic property. It's the substance as a whole. Large dielectric constants help solvents dissolve salts more easily. Large dipole moments also help salts dissolve more easily. However, this needs to be counterbalanced with the size of the molecule. For a solvent to be effective to solvate ions, it's important that, yes, the molecules of the solvent are polar, but also that they are small enough that they can place themselves with the right part of the dipole facing the ion. So if you think of the typical example of the molecule of water would be able to solvate a positive ion from the negative part of the dipole, and would be able to solvate a negative ion using the positive part of the dipole. And it's small enough that it can arrange itself around the molecule, the ions, and solvate them. So a solvent that can do that is small enough, it has a dipole moment, and is small enough that it's able to do that, will be a good solvent for ionic compounds. So for example, if you look at ammonia and dimethyl sulfoxide, although both the dielectric constant and the dipole moment are larger for DMSO, dimethyl sulfide, ammonia is a better solvent for ionic salts just because it is smaller. And if you don't know this, how dimethyl sulfoxide looks like, this is the shape of the dimethyl sulfoxide, and this is the structure of the molecule of ammonia. So the fact that ammonia is smaller makes it a better solvent, even if the values for the relative permittivity and the dipole moment of DMSO are larger, and therefore in principle one could think that it would be a better solvent for ionic compounds.